NOAA confirmed it on January 2nd, 2 weeks before it happens. The strongest geomagnetic storm of January is heading toward Earth, and here's what makes this different. The timing is so precise, so predictable, that forecasters marked January 17th on the calendar weeks ago. That doesn't happen with space weather, not like this. And if you've been following Aurora reports over the past few days, you already know something's happening. Just this week, we experienced a double CME impact, a G2 geomagnetic storm that lit up skies across northern latitudes and pushed auroras into mid-latitude regions. I covered that event in detail in my previous video, those back-to-back solar waves from active region AR4324 hitting Earth within 24 hours. But that was a CME-driven event, rapid, powerful, but less predictable in its timing. What's coming on January 17th is completely different. This isn't a coronal mass ejection, this is a high-speed solar wind stream from a recurring coronal hole. And the key difference? NOAA saw this one coming weeks in advance. They marked it on the calendar, they tracked the pattern through multiple solar rotations, and now we're approaching the date when it unfolds exactly as predicted. Stay with me. In the next few minutes, we're going to walk through exactly what NOAA saw, why January 17th stands out from every other day this month, and what happens when a Kindex 5 geomagnetic storm hits Earth's magnetosphere. This isn't speculation. This is pattern-based science playing out in real time. If you're tracking space weather, if you've noticed the uptick in solar activity, or if you're just trying to understand what's really happening up there, hit that subscribe button right now, because when the 17th arrives, you'll know exactly what you're watching unfold. And trust me, you'll want to be informed before it happens, not scrambling to understand it afterward. So let's break this down from the beginning. On January 2nd, 2026, NOAA's Space Weather Prediction Center released their 27-day space weather outlook. It's a standard document. Every month, forecasters compile solar observations, track active regions, analyze coronal hole positions, and project what Earth's magnetosphere might encounter over the coming weeks. Most of the time, these outlooks read like quiet technical updates, minor disturbances, slight fluctuations, nothing that demands urgent attention, but this one was different. 3 dates jumped out: January 9th through 10th, January 12th through 14th, and January 17th through 18th. Each one flagged for elevated geomagnetic activity, each one tied to the same recurring source, and each one showing progressively stronger conditions. The first 2 dates, the 9th and the 12th, carried Kindex predictions of 4 active conditions. The kind of activity that can stretch auroras a bit further south than usual, create minor disruptions in satellite operations, maybe cause a hiccup or two in high-frequency radio communications. Not negligible, but not alarming either. Forecasters see Kindex 4 activity several times a year during solar maximum. It's part of the rhythm when the sun is active. But January 17th? That carried a Kindex prediction of 5. And that's where the line gets crossed. Kindex 5 isn't just elevated activity. It's the threshold. The point where geomagnetic disturbances officially become storms. It's the difference between your magnetosphere bending under pressure and your magnetosphere being actively compressed. It's when auroras push far enough south that people in northern Europe, Canada, and the northern United States, places that rarely see the lights, suddenly find themselves staring at glowing green curtains rippling across the night sky. It's when satellite operators start monitoring systems more closely, when power grid managers pay attention to fluctuations, when aviation routes get adjusted to avoid polar communication blackouts, when GPS accuracy drifts just enough that precision-dependent systems need recalibration. Kindex 5 is where space weather stops being an abstract curiosity and starts being something that matters on the ground. And NOAA didn't just predict it, they confirmed it with confidence. The language in their outlook wasn't vague, it wasn't hedged with possible or may occur. For January 17th, the wording was direct, likely. High-speed solar wind streams from a recurrent coronal hole, expected Kindex 5, G1 geomagnetic storm conditions. That specificity is rare. Space weather forecasting deals with probabilities, not certainties. Solar wind speed can vary. Coronal mass ejections can fizzle or intensify unexpectedly. Magnetic field orientations shift in transit. There are so many variables between the Sun and Earth that forecasters typically keep their predictions broad and flexible. But when NOAA uses the word likely 2 weeks in advance, it means they're tracking something with pattern-based reliability, something they've seen before, something that's already proven itself predictable, and that something is a coronal hole. Not just any coronal hole, a recurring one that's been rotating into an Earth-facing position on a clock, one that's been sending high-speed solar wind our way for weeks now, one that NOAA has been tracking through multiple solar rotations, watching it align, measuring its output, calculating when it would face Earth again. This is the third time this particular coronal hole has rotated into position. The first time forecasters took note, the second time they confirmed the pattern, and now, on the third rotation, the timing lines up perfectly with solar cycle 25's extended peak activity. That convergence, a proven coronal hole hitting during solar maximum, is why NOAA felt confident enough to mark January 17th on the calendar and call it out specifically in their outlook. So when we talk about January 17th, we're not talking about a random solar flare or an unpredictable outburst. We're talking about a trackable, measurable, repeating event, one that's been building momentum for weeks, one that forecasters have been monitoring closely, one that's now approaching the date for delivering the strongest geomagnetic conditions of the month. And here's the critical piece most people miss when they read these forecasts. This isn't about fear. This isn't about catastrophe. This is about understanding, because space weather, when you know how to read it, becomes less mysterious and more predictable. It stops being something that happens to you and starts being something you can anticipate and prepare for. NOAA's job isn't to scare anyone. Their job is to protect infrastructure, to give satellite operators advance notice, to alert power grid managers, to inform aviation authorities, to provide the public with accurate information so people can make informed decisions, whether that's planning to photograph auroras, adjusting satellite operations, or simply understanding why GPS might be slightly off for a few hours. And right now, that job is pointing every forecaster's attention toward January 17th. Because when a Kindex 5 storm arrives, things change, noticeably, measurably, in ways that are well understood and manageable, measurably, in ways that ripple through technological systems we've built to rely on stable space weather conditions. The question most people have when they first see a forecast like this is simple: should I be worried? And the answer depends on what you mean by worried. If you're asking whether January 17th poses any risk to human health or safety on the ground, the answer is no. Earth's atmosphere and magnetic field are incredibly effective shields. We're protected. A G1 class storm doesn't penetrate to the surface in any harmful way. You won't feel it. Your body won't react to it. There's no risk walking outside, no exposure concern, no health impact whatsoever. But if you're asking whether January 17th represents a shift in space weather conditions that can affect technology, the answer is yes, absolutely. Because while we're safe, the systems we depend on, satellites, power grids, GPS networks, radio communications, operate in environments where geomagnetic storms create very real interference. That's not fear, that's just physics, and understanding that physics is what transforms this from something vague and unsettling into something concrete and manageable. So when NOAA confirmed January 17th on January 2nd, they weren't issuing alarms. They were providing clarity. They were saying, here's what we see. Here's when it's coming, here's what it might affect. Be aware, be prepared, be informed, and that's exactly what we're going to do over the next few minutes. We're going to walk through what makes January 17th different from the other storm dates this month. We're going to explain what a coronal hole actually is and why this particular one has been so reliably trackable. We're going to explore what happens when Kindex 5 conditions hit Earth. We're going to look at the broader context of solar cycle 25 and why right now, late 2025 into 2026, represents one of the most active periods in over a decade. And by the time we're done, January 17th won't feel like a mystery anymore. It'll feel like exactly what it is: a predictable, understandable, scientifically trackable event that you can watch unfold with complete clarity. Because space weather isn't chaos, it's pattern, and once you see the pattern, everything else makes sense. So let's start by understanding what makes January 17th stand apart from the other dates NOAA flagged this month. 3 dates, 3 predictions, but only one of them crossed the threshold. Let's put them side by side for a moment. January 9th through 10th, Kindex 4. January 12th through 14th, Kindex 4. January 17th through 18th, Kindex 5. On the surface, those numbers might not seem drastically different. 1 point on a scale, a minor uptick. But in space weather forecasting, That single point represents a fundamental shift in what's happening to Earth's magnetosphere. Kindex 4 means active geomagnetic conditions. The magnetosphere is responding to incoming solar wind. There's energy transfer happening. The magnetic field lines are bending, flexing, absorbing pressure. You might see auroras at higher latitudes: Alaska, northern Canada, Scandinavia. Satellite operators might note minor fluctuations in drag. Radio communications at high frequencies might experience occasional disruptions. It's noticeable if you're paying attention, but it's not disruptive at scale. Kindex 5 means storm conditions. The magnetosphere isn't just responding anymore, it's being actively compressed. The boundary between Earth's magnetic field and the solar wind, called the magnetopause, gets pushed inward. Energy doesn't just transfer, it floods into the magnetosphere, triggering cascading effects. Auroras don't just brighten at high latitudes, they expand southward, sometimes dramatically. Satellite operations require active monitoring. Power grid managers watch for induced currents. GPS accuracy degrades noticeably. Aviation routes over polar regions get adjusted to avoid communication blackouts. That's the difference. Kindex 4 is space weather activity. Kindex 5 is a geomagnetic storm, and NOAA doesn't use the word storm lightly. So when January 17th showed up in the 27-day outlook with a Kindex 5 prediction, it immediately stood out. Because forecasters weren't hedging. They weren't saying possible storm conditions or elevated activity may approach storm levels. They were saying this is likely, this is what we expect, this is coming. And that confidence came from something specific, something trackable, something that had already proven itself twice before: the source. This isn't a random burst of solar activity. This isn't an unpredictable flare or an unexpected coronal mass ejection. This is high-speed solar wind streaming from a coronal hole, a specific identifiable feature on the Sun that forecasters have been watching rotate into Earth-facing position for weeks. And here's where the pattern becomes undeniable. The coronal hole responsible for January 17th's predicted storm is the same one that caused the activity on January 9th and January 12th. Same source. 3 rotations, escalating conditions. Let me explain how that works. The Sun rotates on its axis roughly every 27 days. That means features on the solar surface, like coronal holes, rotate in and out of Earth-facing positions on that same cycle. If a coronal hole is positioned just right, it can send high-speed solar wind directly toward Earth. Then, 27 days later, that same coronal hole rotates back into position and sends another stream our way. And 27 days after that, it happens again. This is called recurrent geomagnetic activity, and it's one of the most predictable patterns in space weather. The coronal hole we're tracking right now has been through this cycle twice already. The first rotation happened in December. Forecasters noted elevated solar wind speeds. Earth's magnetosphere responded. Minor geomagnetic activity. Kindex 3 to 4 range. Not storm level, but active. Worth watching. 27 days later, the second rotation arrived in early January. The coronal hole was still there. Still active. Still sending high-speed solar wind. And this time, the conditions were stronger. Kindex 4 activity on January 9th. Another pulse is expected around January 12th. The pattern was confirmed. This wasn't a one-time event. This was a recurring source. And now, 27 days after the first rotation, we're approaching the third, January 17th. And this time, the prediction isn't Kindex 4. It's Kindex 5. Storm conditions. Why the escalation? Because coronal holes don't exist in isolation. They interact with the broader solar environment. And right now, that environment is solar cycle 25's extended maximum, a period of heightened activity that's persisting longer and stronger than typical solar cycles. When a coronal hole rotates into position during solar minimum, the surrounding solar environment is relatively quiet. The solar wind it produces interacts with a calmer background. The geomagnetic effects are moderate. But when a coronal hole rotates into position during solar maximum, everything is amplified. The Sun's magnetic field is more complex. Solar wind streams are faster. The background solar wind density is higher. And when high-speed streams from a coronal hole collide with denser, slower solar wind already in transit, they create something called a corrotating interaction region, a compressed zone of turbulence and magnetic complexity that hits Earth's magnetosphere like a wave. That's what's happening with January 17th. The coronal hole itself is the same one we've been tracking, but it's rotating into position during solar cycle 25's peak activity. The solar wind it's sending is interacting with a more turbulent energetic environment, and the result is a stronger, more sustained geomagnetic storm. NOAA's forecasters know this. They've been watching the pattern develop. They've measured the solar wind speeds from previous rotations. They've tracked the coronal hole's position. They've calculated when it would face Earth again, and they've factored in the broader solar environment to predict what happens when that high-speed stream arrives. That's why the January 17th forecast uses the word likely, because this isn't guesswork. This is pattern recognition backed by data. And there's another linguistic clue in NOAA's outlook that reinforces this confidence. When you compare the wording for the 3 January dates, the difference is subtle but significant. For January 9th and 12th, the language is cautious. Active conditions possible. Minor geomagnetic activity expected. The phrasing leaves room for variability. It acknowledges that solar wind conditions can shift in transit, that forecasts can change as new data arrives. But for January 17th, the tone shifts. G1 class storm conditions likely. High-speed solar wind stream from recurrent coronal hole. The language is direct, specific, confidence. That confidence comes from repetition. From having watched this coronal hole rotate through twice already, from having measured its output, from knowing it's still there, still active, and about to face Earth again. And that's what makes January 17th different. It's not just that the Kindex is higher, it's that the Kindex is higher because the pattern is clear, the source is known, the timing is predictable, and the solar environment is primed to amplify the effects. This is space weather forecasting at its most reliable, not a vague prediction based on solar activity trends, not a speculative alert triggered by a distant flare, but a pattern-based forecast grounded in observable, repeating phenomena. And when forecasters have that level of confidence, it means something. It means operators of satellites, power grids, communication networks, and navigation systems can prepare. It means Aurora photographers can plan trips. It means researchers can position instruments to capture data. It means the public can stay informed instead of confused. Because here's what a lot of people don't realize. Space weather forecasting isn't about creating panic. It's about creating clarity, about turning the sun's unpredictable moods into something we can actually track, measure, and anticipate. And January 17th is a perfect example of that. A storm we saw coming weeks ago. A storm with a known source. A storm with predictable timing. A storm that, by the time it arrives, won't feel like a surprise. It'll feel like exactly what NOAA said it would be. But understanding why it's happening and what it means requires digging into the source itself, that recurring coronal hole. The feature on the sun that's been driving this entire pattern. So let's talk about what a coronal hole actually is, why this one has been so reliably trackable, and how a 27-day rotation cycle turns space weather into something surprisingly predictable. So what exactly is a coronal hole, and why does it matter so much that NOAA has been tracking this specific one for weeks? Let's start with what it's not. It's not a literal hole, it's not a gap in the sun's surface, it's not a wound or a tear or some kind of damage. The name is misleading, and I think that's where a lot of confusion starts, because when you hear coronal hole it can sound concerning, but that's not what it means, like the sun has been punctured, but that's not it at all. A coronal hole is a region of the sun's corona, the outermost layer of the solar atmosphere, where the magnetic field behaves differently. Instead of looping back down toward the solar surface in closed magnetic field lines, the field lines in a coronal hole open outward into space. They stretch out, reach beyond the sun, and create a direct pathway for solar wind to escape. Think of it like this. Most of the sun's magnetic field is tangled and looped, closed circuits that trap hot plasma close to the surface. But in coronal holes, those loops don't close. The magnetic field lines point outward, open, unobstructed. And because there's no magnetic barrier holding the plasma back, solar wind flows freely along those field lines, faster, denser, and more consistently than from other regions of the sun. That's why coronal holes matter. They act like highways for solar wind, and when one of those highways points directly at Earth, we're about to get hit by a high-speed stream. The solar wind that comes from coronal holes isn't explosive. It's not a sudden eruption like a solar flare or a coronal mass ejection. It's steady, continuous, a sustained flow of charged particles streaming outward at speeds that can reach 800 kilometers per second, sometimes faster during solar maximum, And here's the key. Because coronal holes are stable features that last for weeks or even months, and because the Sun rotates on a 27-day cycle, a coronal hole in the right position will face Earth roughly every 27 days, over and over, like clockwork. That's what we're dealing with right now, a coronal hole that's been stable enough to survive multiple rotations, one that's positioned in a way that, every 27 days it rotates back into Earth-facing alignment and sends another high-speed solar wind stream our way. This is the third rotation. And NOAA has been tracking it the entire time. The first time this coronal hole rotated into position, forecasters noticed elevated solar wind speeds, not extreme, but consistent. High enough to trigger minor geomagnetic activity at active levels. Auroras brightened at high latitudes. Satellite operators noted slight increases in atmospheric drag. Nothing alarming, but definitely noticeable. Forecasters took note. They marked the coronal hole's position, they measured its size and magnetic structure, and they calculated when it would face Earth again. 27 days later, early January, the coronal hole rotated back, and just as predicted, solar wind speeds spiked again. January 9th brought Kindex 4 activity. A few days later, on January 12th, another pulse arrived. Same source, same pattern. The coronal hole was still there, still active, still sending high-speed streams. That's when NOAA's confidence solidified. This wasn't a one-time event. This was recurrent geomagnetic activity driven by a stable, trackable coronal hole, and that meant they could predict the next rotation with a high degree of certainty. 27 days after the first rotation, 14 days after the second pulse, the math pointed to January 17th. And when forecasters looked at the broader solar environment, solar cycle 25's extended maximum, elevated background solar wind, increased magnetic complexity, they knew this third rotation wasn't going to be just another Kindex 4 event, it was going to cross the threshold, Kindex 5. Storm conditions, and that's exactly what they put in the 27-day outlook. Now here's why this pattern matters beyond just prediction accuracy. Coronal holes don't behave like other solar phenomena. Solar flares are sudden and unpredictable. Coronal mass ejections can change trajectory or dissipate before reaching Earth. But coronal holes, they're persistent, stable, and because they're driven by the Sun's magnetic field structure, they often last for multiple solar rotations, sometimes for months. That persistence is what makes them such reliable sources of recurrent geomagnetic activity. And during solar maximum, when the Sun's magnetic field is more complex and dynamic, coronal holes can become even more effective at channeling high-speed solar wind. The coronal hole we're tracking right now is a perfect example. It's been stable enough to survive at least 3 rotations. It's positioned at a solar latitude that brings it into Earth-facing alignment every 27 days. And it's active enough that the solar wind it produces consistently triggers geomagnetic responses when it reaches Earth. But here's the part that really demonstrates the power of pattern-based forecasting. This isn't the first time NOAA has tracked a recurrent coronal hole through multiple rotations. It happens several times during every solar cycle. Forecasters know the signs, they know what to look for, they know how to calculate rotation timing, and they know how to predict when a coronal hole that caused geomagnetic activity during one rotation is likely to do it again. That's why the January 17th forecast wasn't a guess. It was a calculated projection based on observed patterns. And it's why, when January 17th arrives, we'll be watching a storm that was weeks in the making, not because something went wrong with the Sun, but because something went right with our ability to understand and predict what the Sun does. So when you see the term coronal hole in space weather forecasts, think of it as a natural solar feature. Think of it as a feature, a predictable, trackable, scientifically understandable feature that allows forecasters to do their jobs with a level of accuracy that wasn't possible even a decade ago. And the coronal hole responsible for January 17th? It's been a textbook case. Stable, recurrent, measurable, exactly the kind of solar feature that turns space weather forecasting from speculation into science. But there's another layer to this that we haven't touched on yet. The fact that this is the third rotation matters for more than just prediction timing. Because each rotation doesn't happen in isolation. The solar environment changes between rotations, and when a coronal hole rotates into position during solar maximum, especially during solar cycle 25's extended peak, the conditions it creates are amplified by everything else happening on the Sun. That amplification is why January 17th is predicted to reach Kindex 5 while the earlier rotation stayed at Kindex 4. The coronal hole itself is roughly the same. The solar wind speed it produces is similar. But the environment that solar wind is moving through, that's different. During the first rotation in December, the background solar environment was relatively calm. Solar cycle 25 was active, but not at peak levels yet. The solar wind from the coronal hole travelled through a fairly stable medium and arrived at Earth without much additional turbulence. During the second rotation in early January, activity had picked up. The Sun was approaching its extended maximum. The background solar wind was denser, and when the high-speed stream from the coronal hole interacted with that denser environment, it created more pronounced geomagnetic effects. Still Kindex 4, but stronger than the first rotation. Now for the third rotation on January 17th, we're squarely in the middle of solar cycle 25's peak activity. The Sun's magnetic field is highly complex. Active regions are scattered across the solar surface. The background solar wind is faster and more variable, and when the high-speed stream from the coronal hole arrives, it's going to collide with all of that, creating a compressed, turbulent interaction region that hits Earth's magnetosphere with more force than the previous two rotations. That's the convergence. That's why forecasters are confident this rotation will push conditions into storm territory. It's not just the coronal hole. It's the coronal hole plus the timing plus the broader solar environment. And when all of those factors align, the result is predictable. Stronger geomagnetic activity. Kindex 5. G1 class storm conditions. And here's the fascinating part. This kind of pattern recognition is exactly how space weather forecasting has evolved over the past 2 decades. Forecasters don't just look at individual events anymore. They look at patterns, cycles, recurring phenomena. They track coronal holes through multiple rotations. They monitor how solar wind streams interact with the broader environment. They calculate probabilities based on historical data and real-time observations. And the result is forecasts that are more accurate, more reliable, and more useful than ever before. January 17th is proof of that. A storm predicted 2 weeks in advance based on a coronal hole that's been tracked for weeks. A forecast grounded in repeating patterns and measurable data. A prediction that, by the time the storm arrives, will feel less like a surprise and more like confirmation of what the science already told us. But understanding the coronal hole is only part of the story. Because the real significance of January 17th isn't just that it's the third rotation, it's that this third rotation is happening during one of the most active periods of solar cycle 25. And to understand why that matters, we need to zoom out and look at the bigger picture of what's been happening with the Sun over the past year. 3 rotations, same coronal hole. But January 17th stands apart for a reason that goes beyond just timing. Let me walk you through what forecasters saw with each rotation, because understanding the progression is key to understanding why this third one matters so much. The first rotation was identified during routine solar observations. The coronal hole was positioned to send high-speed solar wind directly toward Earth. It wasn't the largest coronal hole on the Sun. It wasn't the most magnetically complex, but it was positioned in a way that made forecasters pay attention, right in the path of Earth's orbital trajectory, aligned to send high-speed solar wind directly our way when it rotated into position. When the solar wind stream from that first rotation arrived, Earth's magnetosphere responded predictably. Geomagnetic activity increased, Kindex 3 to 4. Minor fluctuations in satellite operations, auroras brightening at higher latitudes, standard mid-cycle space weather activity. Nothing that triggered alerts or required operational changes for most systems. But forecasters didn't just note the activity and move on. They logged the coronal hole's position, they measured the solar wind speed and density, they tracked its magnetic structure, and most importantly, they calculated when it would rotate back into Earth-facing position. 27 days, that's the clock, the Sun's rotation period, and if the coronal hole remained stable, it would face Earth again in late December or early January. Rotation 2 arrived right on schedule. Early January 2026. The coronal hole had survived. It was still there, still active, still sending high-speed solar wind, and this time the effects were slightly stronger. January 9th through 10th brought Kindex 4 activity. A few days later, another pulse hit on January 12th. Same source, same pattern, but with noticeably more impact. Satellite drag increased more than during the first rotation. Auroras pushed further south. Power grid operators in northern regions noted minor fluctuations in voltage levels. GPS accuracy drifted slightly more than usual. Still not storm conditions, still Kindex 4, but stronger, more sustained. And that's when forecasters knew. This wasn't just a 2-rotation event. The coronal hole was persistent. It was stable, and it was showing no signs of dissipating, which meant a 3rd rotation was coming. And based on the trend, slightly stronger activity with each pass, forecasters started factoring in what the 3rd rotation might bring. That's where solar cycle 25's timing becomes critical. December 2025 was active, but the sun hadn't yet reached its extended maximum. January 2026? That's different. We're now in the heart of solar cycle 25's peak activity, a period that's not only stronger than typical cycles, but also lasting longer. Most solar cycles have a relatively sharp peak. Activity ramps up, hits maximum, and then declines over the course of a year or two. But solar cycle 25 is showing a double peak phenomenon, an extended maximum that's persisting through late 2025 into 2026, and is expected to continue into 2027. That means instead of a brief window of heightened activity, we're experiencing a prolonged period where the sun is consistently energetic, magnetically complex, and producing elevated solar wind conditions. And when a recurrent coronal hole rotates into position during that kind of environment, the effects are amplified. Here's why. The solar wind from the coronal hole doesn't travel through empty space. It moves through an existing solar wind environment that's already flowing outward from the sun. During solar minimum, that background wind is relatively calm, slow, low density. When a high-speed stream from a coronal hole enters that environment, it creates a clean, predictable interaction. But during solar maximum, especially during solar cycle 25's extended peak, the background solar wind is faster, denser, and more turbulent. Active regions on the sun are constantly sending out their own solar wind streams. Coronal mass ejections occasionally disrupt the flow. And when a high-speed stream from a coronal hole enters that environment, it doesn't just flow smoothly. It collides with slower wind ahead of it, compresses, and forms what's called a corrotating interaction region. Think of it like faster traffic catching up to slower traffic. The high-speed stream is moving at higher velocity. The background solar wind is moving slower. When they meet, there's compression, turbulence, a shock wave of energy that propagates outward. And when that compressed, turbulent region hits Earth's magnetosphere, the geomagnetic response is significantly stronger than it would be from the high-speed stream alone. That's what's happening with January 17th. The coronal hole is sending the same high-speed solar wind it sent during the first 2 rotations, but this time, the background environment is primed. Solar cycle 25 is at peak activity. The solar wind the coronal hole is moving through is more complex, and when that high-speed stream collides with the existing environment and reaches Earth, it's going to create stronger, more sustained geomagnetic storm conditions. Kindex 5, storm level, G1 class, that's the convergence. That's the 3rd rotation pattern, same source, same timing, but amplified by the broader solar environment. And here's the part that really underscores NOAA's confidence in this forecast. They've seen this before, not with this specific coronal hole, but with recurrent coronal holes during previous solar cycles. They know how the pattern plays out. They know that when a stable coronal hole rotates through multiple times during solar maximum, the 3rd or 4th rotation often produces the strongest geomagnetic effects, because by that point the solar environment has fully ramped up, the amplification factors are in place, and the interaction between the high-speed stream and the background wind is at its most intense. That's why the January 17th forecast isn't speculative, it's pattern-based. Forecasters looked at the first 2 rotations, they measured the escalation, they factored in solar cycle 25's current activity levels, and they projected what happens when that same coronal hole rotates back one more time. The math said Kindex 5, the observation supported it, the historical patterns confirmed it, and NOAA put it in writing. Now here's what that means practically. January 17th isn't going to come out of nowhere, is not going to catch anyone off guard. By the time the high-speed solar wind stream arrives, satellite operators will have had weeks to prepare. Power grid managers will be monitoring systems closely. Aviation authorities will have adjusted polar routes. Aurora photographers will have planned trips. and anyone tracking space weather will know exactly what's happening and why. That's the value of pattern recognition in space weather forecasting. It transforms unpredictability into preparation. It turns a chaotic solar environment into something we can actually track and understand. And the third rotation pattern is one of the clearest examples of that. Because when you watch a coronal hole rotate through once, twice, 3 times, each time producing slightly stronger effects as the solar environment intensifies, you're not watching randomness. You're watching physics, predictable, measurable, scientifically understandable physics. January 17th is the result of that physics playing out over weeks, a coronal hole that's been stable enough to persist, a 27-day rotation cycle that brings it back into alignment, and a solar environment, solar cycle 25's extended maximum, that amplifies the impact of that third rotation beyond what the first two produced. That convergence is why NOAA called it out specifically, why they used confident language, why they marked it on the calendar 2 weeks in advance. Because when pattern, timing, and solar environment align like this, the outcome becomes clear. And that clarity is exactly what space weather forecasting is designed to provide. Not fear, not confusion, just accurate, reliable information that allows everyone, from infrastructure operators to curious observers, to understand what's coming and why. But to fully appreciate why January 17th carries that Kindex 5 prediction, we need to talk about the broader context. Solar cycle 25 itself. Because this isn't just any solar cycle. This is one of the most active, most prolonged, most scientifically interesting solar cycles we've seen in over a decade. And understanding what makes solar cycle 25 different is essential to understanding why right now, January 2026, represents a peak moment for space weather activity. Solar cycle 25 wasn't supposed to be this active. When solar physicists first projected what this cycle would look like, the consensus was moderate, not weak, but not exceptionally strong either. A middle-of-the-road cycle that would ramp up, peak, and decline over the standard timeframe. Nothing to suggest we'd be seeing the kind of extended, intense activity that's been unfolding since late 2024. But the sun doesn't always follow predictions, and solar cycle 25 has surprised researchers at nearly every turn. The cycle officially began in December 2019. That's when the sun transitioned from solar minimum, the quiet phase where sunspots are rare and solar activity is minimal, into the early stages of ramping up toward maximum. For the first couple of years, everything looked predictable. Sunspot numbers gradually increased, solar flares became more frequent, coronal holes appeared and rotated through, standard solar cycle behavior. But by 2023, something started becoming clear. Solar cycle 25 was accelerating faster than expected. Sunspot numbers were exceeding projections. Solar flares were more intense and more frequent. Coronal mass ejections were occurring regularly, and by mid-2024 it was undeniable. This wasn't a moderate cycle. This was an active cycle. One that was not only stronger than the initial predictions, but also showing signs of something unusual, a double peak. Most solar cycles have a single, relatively defined maximum. Activity ramps up, hits a peak that lasts for a few months, and then begins declining over the next year or two. But some cycles, the more active, magnetically complex ones, exhibit a double peak. 2 distinct periods of heightened activity separated by a brief lull, creating an extended maximum that can last for 2 years or more. Solar cycle 25 is showing exactly that pattern. Solar maximum was reached in October 2024. Sunspot numbers surged, solar flares spiked, coronal mass ejections became almost routine, and geomagnetic storms reached G3 and G4 levels multiple times, strong enough to push auroras deep into mid-latitudes and trigger significant operational impacts on satellites and power grids. Then, for a brief period in early 2025, activity dipped slightly. Not back to solar minimum levels, but noticeably quieter than the late 2024 surge. For a moment it looked like the cycle might be transitioning toward its decline phase, but by summer 2025 activity ramped up again. Sunspot numbers climbed back toward peak levels, solar flares resumed at high frequency, and by late 2025 it became clear solar cycle 25's second peak was underway. And it was matching, if not exceeding, the intensity of the first. That second peak is where we are right now, January 2026. and this second peak is expected to persist through most of 2026 and into early 2027, creating an extended window of elevated solar activity that's giving forecasters consistent high-quality data to work with, and giving Earth's magnetosphere consistent high-intensity solar wind to respond to. This extended maximum is exactly why the third rotation of the coronal hole we've been tracking matters so much. Because when a recurrent coronal hole rotates into position during solar minimum, the geomagnetic effects are moderate. But when that same coronal hole rotates through during an extended solar maximum, especially one as active as solar cycle 25's second peak, the effects are amplified significantly. The background solar wind is faster, the solar wind density is higher, the magnetic field structure is more complex, and all of those factors combine to create stronger, more sustained geomagnetic storm conditions when the high-speed stream from the coronal hole arrives. That's the convergence happening on January 17th. A stable coronal hole, a predictable 27-day rotation, and a solar environment that's primed to amplify the geomagnetic impact. But solar cycle 25's significance goes beyond just January 17th. Because this extended maximum means we're not just dealing with one isolated event. We're in a period where recurrent geomagnetic activity is the norm, where coronal holes rotating through multiple times is expected, where G1 class storms, and occasionally stronger, are regular occurrences rather than rare anomalies. For space weather researchers, this is an incredibly valuable period. The data being collected right now will inform models and forecasts for decades. For satellite operators, power grid managers, and communication network authorities, this is a period that demands vigilance but also demonstrates the effectiveness of preparation. And for the general public, this is a period where space weather stops being an abstract concept and becomes something observable, understandable, and even tangible, through auroras, through occasional GPS disruptions, through the awareness that the sun is an active, dynamic presence that directly affects the technological systems we rely on. And here's what makes solar cycle 25 particularly fascinating from a scientific perspective. The double peak structure it's exhibiting is closely tied to the sun's magnetic field dynamics. The sun doesn't have a single magnetic field like Earth does. It has multiple overlapping magnetic regions that shift, merge, and reorganize over the course of a solar cycle. During solar minimum, those regions are relatively simple and organized. During solar maximum, they become chaotic and complex. In a single peak cycle, that complexity ramps up quickly, peaks, and then declines as the magnetic field reorganizes into a simpler structure. But in a double peak cycle, the magnetic field doesn't fully reorganize after the first peak. Instead, it maintains its complexity, shifts slightly, and then surges again, creating a second peak of activity before finally settling down. Solar cycle 25's double peak suggests that the sun's magnetic field is undergoing a particularly complex reorganization, and that complexity is directly reflected in the space weather we're experiencing. More coronal holes, more solar flares, more coronal mass ejections, and more recurrent geomagnetic activity driven by persistent features like the coronal hole responsible for January 17th. That persistence is key, because when the sun's magnetic field is highly complex, features like coronal holes can last for months instead of weeks. They can survive multiple rotations without dissipating, and they can continue producing high-speed solar wind streams that reach Earth over and over, creating the kind of recurrent patterns that make forecasting possible. That's what we've been seeing throughout late 2025 and into early 2026. Coronal holes that persist, solar wind streams that repeat, geomagnetic activity that follows 27-day cycles. It's not random, it's not chaotic. It's the sun's magnetic field expressing itself in a way that's predictable, trackable, and scientifically rich. And for anyone tracking space weather right now, this is the period to be paying attention. Because solar cycle 25's extended maximum isn't going to last forever. By late 2027 or early 2028, activity will begin declining as the sun transitions back towards solar minimum. Coronal holes will become less persistent, solar wind streams will weaken, geomagnetic storms will become less frequent. But right now we're in the thick of it, and January 17th is a snapshot of what that looks like. A predictable geomagnetic storm driven by a recurrent coronal hole during one of the most active periods of one of the most active solar cycles in recent memory. That's the broader context. That's why this moment matters. Not because January 17th represents a catastrophe or a crisis, but because it represents a clear, measurable example of how space weather works when the sun is at its most active. And when the sun is this active, understanding what's happening stops being optional. It becomes essential. Because space weather during solar maximum doesn't just affect scientific instruments or high-altitude satellites. It affects GPS systems, power grids, aviation routes, communication networks, radio signals, auroras, all of it. And the more we understand how solar cycles work, how coronal holes behave, how solar wind streams interact, how geomagnetic storms develop, the better prepared we are to manage those effects. Solar Cycle 25 is giving us a masterclass in space weather. And January 17th is one lesson in that class. A predictable, trackable, understandable event that demonstrates exactly how the sun, the solar wind, and Earth's magnetosphere interact when conditions align. But understanding the cycle and the coronal hole only gets us so far. The real question most people have when they hear about a Kindex 5 geomagnetic storm is simple. What does that actually mean for Earth? What happens when that high-speed solar wind stream hits our magnetosphere? What changes? What gets disrupted? What can we see? And that's exactly what we need to explore next. So the high-speed solar wind stream is on its way. It's been tracked for weeks. The coronal hole has rotated into position, and on January 17th, Earth's magnetosphere is going to get hit with Kindex 5 conditions. What does that actually mean? Let's start with the basics. Earth's magnetosphere is our planet's first line of defense against the solar wind. It's a massive, invisible bubble created by Earth's magnetic field that extends tens of thousands of kilometers into space. On the side facing the sun, the magnetosphere is compressed by the constant pressure of the solar wind. On the night side, it stretches out into a long tail, and under normal conditions, that structure is stable. The solar wind flows around it like water flowing around a rock in a stream. But when a high-speed solar wind stream arrives, especially one carrying the right magnetic field orientation, that stability gets disrupted. The solar wind doesn't just flow around the magnetosphere anymore, it compresses it. The magnetopause, the boundary between Earth's magnetic field and the solar wind, gets pushed inward. Energy from the solar wind transfers into the magnetosphere, and that energy doesn't just sit there, it cascades through the entire system, triggering a series of effects that ripple from space down to the upper atmosphere. That cascade is what we call a geomagnetic storm, and Kindex 5 means we're in G1 class storm territory, the first level of geomagnetic storming. Not the strongest, G5 is the maximum, but strong enough that the effects are noticeable, measurable, and operationally significant. Let's walk through what happens. First, the magnetosphere compresses. When the high-speed solar wind hits, the pressure on the sunward side of the magnetosphere increases. The magnetopause, which normally sits around 60,000 kilometers from Earth, gets pushed inward, sometimes as close as 40,000 kilometers. That compression stores energy in the magnetic field lines, bending them, stretching them, loading them with tension. Eventually that tension releases, and when it does, the energy doesn't just dissipate, it flows along magnetic field lines into the polar regions, channeling into Earth's ionosphere, the upper layer of the atmosphere where charged particles interact with the magnetic field. That's where auroras happen. Auroras are the most visible effect of a geomagnetic storm, and during Kindex 5 conditions, they don't just appear at the poles, they expand. The auroral oval, the ring-shaped zone where auroras typically occur, stretches southward in the northern hemisphere and northward in the southern hemisphere. Places that rarely see auroras suddenly find themselves under glowing curtains of green, red, and purple light. During a G1 class storm, auroras can be visible as far south as northern Europe, Canada, and the northern United States. Sometimes even further if conditions are just right. And the auroras themselves tend to be more dynamic during storms. Not just static glows, but moving, rippling, dancing structures that shift and pulse in response to the energy flooding into the ionosphere. For aurora photographers and enthusiasts, Kindex 5 is exactly the kind of condition they watch for. It's the threshold where auroras become accessible to people who don't live in the Arctic. Where a short drive north can put you under lights you might only see a few times a year. But auroras are just the visible part of the story, because while the energy is creating those beautiful displays in the sky, it's also affecting systems that rely on stable space weather conditions. Satellites are the first to feel the impact. When a geomagnetic storm hits, the upper atmosphere heats up and expands. That expansion increases atmospheric drag on satellites in low Earth orbit, and that drag, even though it's incredibly thin at those altitudes, is enough to slow satellites down slightly, alter their orbits, and require operators to make adjustments. For most satellites, a G1 class storm isn't a crisis. Drag increases are manageable, orbit corrections are routine, but it's not negligible either. Satellite operators have to monitor systems more closely. Fuel reserves get used for station-keeping maneuvers, and for satellites that are already low on fuel or operating at end of life, even minor drag increases can accelerate deorbiting timelines. Communication systems also feel the effects. The ionosphere, which normally reflects and refracts radio signals in predictable ways, becomes turbulent during geomagnetic storms. That turbulence can disrupt high-frequency radio communications, especially over polar regions where the magnetic field lines channel the most energy. Aviation routes that cross polar regions, flights between North America and Asia for example, often rely on high-frequency radio for communication when they're out of range of ground-based systems. During a geomagnetic storm, those communications can become unreliable. Static increases, signal clarity degrades, and in some cases flights are rerouted to lower latitudes where communication conditions are more stable. It's not a safety issue. Aviation systems have redundancy built in, but it is an operational impact. Routes get adjusted, flight times increase slightly, and passengers on affected flights might notice the detour if they're tracking their flight path. GPS is another system that responds to geomagnetic storms. GPS satellites operate in medium Earth orbit, well above the atmospheric drag effects that low Earth orbit satellites experience. But GPS signals have to pass through the ionosphere to reach receivers on the ground, and when the ionosphere is turbulent, those signals get delayed, refracted, and degraded. For most consumer GPS applications, navigation apps on your phone, car GPS systems, the degradation during a G1 class storm is minimal. You might notice slightly slower position updates or occasional drift, but nothing that makes the system unusable. But for precision GPS applications, surveying, precision agriculture, autonomous vehicles, scientific instruments, even small degradations matter. Accuracy that's normally within centimeters can drift to meters, and that's enough to require recalibration, delays, or switching to alternative positioning methods. Power grids are the system most people worry about when they hear about geomagnetic storms, and that concern is justified, but mostly for stronger storms. G1 class storms can induce currents in power lines, especially in high latitude regions where the magnetic field lines channel the most energy. Those currents, called geomagnetically induced currents, can create voltage fluctuations, affect transformer performance, and in extreme cases damage equipment. But during a G1 class storm, those effects are minor. Power grid operators monitor systems more closely. They might adjust loads or reroute power to minimize stress on transformers, but blackouts, grid failures, those are risks associated with G3 class storms and higher. Kindex 5 doesn't push us into that territory. So when we talk about what happens on January 17th, we're talking about noticeable impacts but not catastrophic ones. Auroras expanding southward, satellite operators making routine adjustments, aviation routes shifting slightly, GPS accuracy drifting a bit, power grid managers staying alert. None of that is cause for panic, but all of it is reason for awareness. Because here's the reality. Our modern technological infrastructure was built assuming stable space weather conditions. Satellites were designed for predictable atmospheric drag. GPS was calibrated for a stable ionosphere. Power grids were engineered for consistent magnetic field conditions, and most of the time those assumptions hold. Space weather is quiet more often than it's active, but during solar maximum, and especially during periods like Solar Cycle 25's extended peak, those assumptions get tested. Geomagnetic storms become frequent. Space weather conditions shift from stable to turbulent on a regular basis, and systems that were designed with those assumptions have to adapt. That adaptation is exactly why space weather forecasting exists, why NOAA monitors the sun 24/7, why forecasters track coronal holes through multiple rotations, why predictions like the January 17th outlook get issued 10 days in advance. Because when you know a storm is coming, you can prepare. Satellite operators can plan maneuvers, aviation authorities can adjust routes, Power grid managers can monitor systems. GPS users can be aware of potential accuracy issues. Aurora photographers can plan trips, and the general public can stay informed instead of confused. That's the real value of understanding what Kindex 5 means. Not to create fear, but to create clarity. To transform a vague, unsettling concept, geomagnetic storm, into something concrete and manageable. Something that has real effects, yes, but effects that are understandable, predictable, and well within the range of what our infrastructure is designed to handle. Because the sun isn't attacking Earth when it sends a high-speed solar wind stream our way, the magnetosphere isn't failing when it compresses under solar wind pressure, satellites aren't breaking when atmospheric drag increases, power grids aren't collapsing when geomagnetically induced currents flow through transmission lines. These are natural interactions between the sun and Earth, physics playing out on a planetary scale. And while those interactions create challenges for technological systems, they're challenges we've learned to anticipate, manage, and adapt to. January 17th will be another example of that, a geomagnetic storm that arrives exactly when forecasters said it would. A storm with effects that are predictable and manageable. A storm that for most people will be completely invisible, unless they're watching auroras, tracking space weather dashboards, or paying attention to the systems that quietly adapt to keep everything running smoothly. And that's the balance space weather creates. Beautiful auroras on one hand, operational impacts on the other, both real, both measurable, both part of the same phenomenon. But January 17th isn't the only date worth watching this month, because remember, NOAA flagged 3 dates in their 27-day outlook, and while the 17th is predicted to be the strongest, the 2 earlier dates, January 9th and January 12th, are still worth understanding. They're part of the same pattern, same coronal hole, same rotation cycle, just slightly weaker conditions, and those earlier storms can tell us a lot about what to expect when the 3rd rotation arrives. January 17th is the main event, but it's not the only event. Let's go back to those other 2 dates NOAA flagged in the 27-day outlook, January 9th through 10th, January 12th through 14th. Both predicted to bring Kindex 4 active geomagnetic conditions, both driven by the same recurrent coronal hole that's going to deliver Kindex 5 on the 17th. Think of them as warm-ups, previews, dress rehearsals for the main performance, and they're worth paying attention to because what happens on the 9th and the 12th will give us a clear picture of what to expect and how much stronger conditions will be when the 17th arrives. January 9th through 10th marks the first pulse from the coronal hole's 2nd rotation. High-speed solar wind streaming toward Earth, Kindex 4 predicted. Active geomagnetic conditions without crossing into storm territory. What does that mean practically? Auroras will brighten at higher latitudes. Alaska, northern Canada, Scandinavia, Iceland, places that regularly see auroras, will experience more intense displays than usual. The auroral oval will stretch slightly southward, but not far enough to reach mid-latitude regions. If you're in northern Scotland, you might catch a faint glow on the northern horizon. If you're in Seattle or Oslo, probably not, unless conditions exceed predictions. Satellite operators will note increased atmospheric drag, minor adjustments to orbit maintenance, nothing requiring emergency maneuvers, but enough that mission controllers will be monitoring systems more closely than during quiet conditions. GPS accuracy might drift slightly in polar regions. Communication systems operating at high frequencies might experience occasional disruptions. Power grids in high-latitude areas might see minor fluctuations in geomagnetically induced currents. All of that falls within Kindex 4 territory, noticeable if you're watching for it, operationally relevant if you manage systems affected by space weather, but not disruptive at a large scale. Then, a couple of days later, January 12th through 14th brings another pulse. Same coronal hole, another stream of high-speed solar wind, another Kindex 4 prediction. Why 2 pulses from the same rotation? Because coronal holes don't send solar wind in a single, uniform stream. The wind speed varies across the coronal hole's surface. Some regions produce faster streams than others, and as the sun rotates and the coronal hole moves across Earth-facing position, those variations create multiple pulses of elevated solar wind, each one triggering its own geomagnetic response. That's why NOAA's outlook flagged 2 separate windows for the 2nd rotation. January 9th catches the leading edge of the high-speed stream. January 12th catches the peak or trailing edge. Together they represent the full geomagnetic impact of the coronal hole's 2nd Earth-facing rotation. And here's why those two dates matter beyond just being space weather events themselves. They're benchmarks, reference points. Because forecasters have been tracking this coronal hole through multiple rotations, they can compare the strength of each rotation and watch for trends. If the second rotation produces stronger Kindex 4 conditions than the first rotation did, that tells forecasters the coronal hole is still active, still producing robust solar wind, and still capable of triggering significant geomagnetic responses. And that information directly informs the prediction for the third rotation, which is exactly what happened. The second rotation in early January produced noticeably stronger effects than the first rotation in December, not just by forecasters' measurements, but by observable impacts. Auroras were more intense, satellite drag was more pronounced, geomagnetic fluctuations were more sustained. That escalation confirmed what forecasters already suspected. The coronal hole wasn't weakening, it was maintaining its strength, and with solar cycle 25's extended maximum amplifying conditions, the third rotation wasn't going to just match the second, it was going to exceed it. That's the progression. Kindex 34 in December, Kindex 4 in early January, Kindex 5 predicted for January 17th. Each rotation slightly stronger as the solar environment intensifies, and that progression is exactly what makes the January 9th and 12th events valuable to watch. Because they're not just isolated space weather days, they're part of a pattern, and observing how the magnetosphere responds to those Kindex 4 conditions will give us context for understanding how it responds when Kindex 5 hits. If auroras on the 9th reach a certain latitude, we can expect them to reach further south on the 17th. If satellite drag increases by a measurable amount on the 12th, we can expect a larger increase on the 17th. If GPS accuracy drifts slightly during the earlier events, we can anticipate more noticeable drift during the main event. That's the beauty of recurrent geomagnetic activity. It's not random, it's structured, and each rotation gives us more data, more understanding, more ability to predict what comes next. For anyone tracking space weather in real time, and there are thousands of people who do, the 9th and 12th are opportunities. Opportunities to test equipment, to practice observation techniques, to see how systems respond under active conditions before the stronger storm arrives. Aurora photographers, for example, can use the 9th and 12th to scout locations, test camera settings, and gauge how far south auroras might reach during Kindex 4 conditions. Then, when the 17th arrives with Kindex 5, they'll know exactly where to position themselves for the best chance of capturing more intense displays. Satellite operators can use the earlier dates to observe how their specific systems respond to increased drag and ionospheric turbulence. That information helps them plan more precise adjustments for the 17th. Power grid managers can monitor geomagnetically induced currents during the 9th and 12th, establishing baselines for what to expect when stronger conditions hit on the 17th. And for the general public, the 9th and 12th are reminders that space weather is active right now, that solar cycle 25's extended maximum is delivering consistent geomagnetic activity, that the sun isn't some distant, unchanging object, it's dynamic, energetic, and directly connected to what happens in Earth's magnetosphere. So while January 17th is the date NOAA highlighted with the strongest prediction, the 9th and 12th are far from insignificant. They're part of the same story, the same coronal hole, the same 27-day cycle, just different chapters in a progression that's been unfolding for weeks, and by the time the 17th arrives, anyone who's been paying attention will have already seen the preview. They'll understand the pattern, they'll know what Kindex 4 looks like, and they'll be able to appreciate exactly how much stronger Kindex 5 is when it finally hits. Because that's the advantage of pattern-based forecasting. It doesn't just tell you what's coming, it shows you the progression, the build-up, the context. And that context transforms a single date, January 17th, from an isolated event into the culmination of weeks of observable, trackable space weather activity. But understanding the dates is only part of the equation, because when January 17th actually arrives, there are specific things to watch for, specific ways the storm will manifest, specific opportunities to observe and understand what's happening in real time. January 17th is 10 days away, and when it arrives, there are specific things you can watch for. Observable effects, measurable changes, ways to see space weather playing out in real time. Let's start with auroras, because they're the most accessible way for anyone to observe a geomagnetic storm. During Kindex 5 conditions, the auroral oval expands significantly. In the northern hemisphere, auroras that normally stay confined to the Arctic Circle can push as far south as northern Europe, Canada, and the northern United States. We're talking about auroras visible from places like northern Scotland, southern Norway, most of Canada, and potentially even the northern edges of states like Montana, North Dakota, Minnesota, and Maine. For people living at those latitudes, January 17th through 18th could offer one of the best aurora viewing opportunities of the winter season, and because this storm is predicted in advance, there's time to plan, to check local weather forecasts, to find dark sky locations away from city lights, to prepare camera equipment if you're interested in photography. But timing matters. Geomagnetic storms aren't instantaneous. When the high-speed solar wind stream arrives, the magnetosphere takes time to respond. The energy build-up, the compression, the release, it all unfolds over hours. And auroras tend to be most intense during the late evening and overnight hours when you're on the night side of Earth, looking toward the magnetic poles. So if you're planning to watch for auroras on January 17th, focus on the evening of the 17th into the early morning hours of the 18th. That's when conditions are most likely to produce visible displays at extended latitudes. And here's a practical tip. Aurora visibility depends as much on local weather as it does on geomagnetic conditions. A strong geomagnetic storm is useless if clouds are blocking your view. So check cloud forecasts for your area. If skies are expected to be clear on the 17th, you've got a solid chance. If clouds are rolling in, you might need to adjust your location, or accept that this particular storm might not be visible from your area, even if the geomagnetic conditions are perfect. For those of you who aren't at latitudes where auroras will be visible, there are still ways to track what's happening. Real-time space weather monitoring is surprisingly accessible. NOAA's Space Weather Prediction Center provides public dashboards that show current solar wind conditions, magnetometer readings, and Kindex values as they update. You can watch the high-speed solar wind stream arrive, you can see the magnetosphere respond, you can track the exact moment Kindex values cross from 4 to 5. It's fascinating to watch, even if you're not directly experiencing the effects, because you're seeing raw data from spacecraft monitoring the sun, from satellites measuring Earth's magnetic field, from ground-based magnetometers tracking geomagnetic fluctuations. You're watching space weather science in action. And if you want to go deeper, there are Aurora forecast websites and apps that provide predictions for auroral visibility based on current geomagnetic conditions. These tools show the expected auroral oval position in real time, updated every few minutes. If you're near the edge of the predicted visibility zone, those updates can tell you whether it's worth stepping outside to check, or whether conditions haven't quite reached your latitude yet. Beyond auroras, there are other observable effects worth noting, though most of them are more subtle and require specialized equipment or attention to specific systems. If you use GPS regularly, especially precision GPS, January 17th is a day to be aware of potential accuracy drift. For casual navigation, you probably won't notice anything. But if you're doing surveying work, using GPS for scientific measurements, or relying on centimeter-level accuracy, recalibrate your equipment after the storm passes and double-check any measurements taken during peak geomagnetic activity. If you're involved in aviation, either as a pilot or just tracking flights, watch for route adjustments on polar flights. Flights between North America and Asia, or Europe and the Pacific, often cross polar regions where high-frequency radio communication is critical. During geomagnetic storms, some of those flights get rerouted to lower latitudes to maintain reliable communication. Flight tracking websites will show those adjustments in real time if they occur. If you operate radio equipment, amateur radio, shortwave listening, anything relying on high-frequency ionospheric propagation, January 17th might bring noticeable disruptions. Signal clarity can degrade. Propagation paths can shift. Static increases. For radio enthusiasts, geomagnetic storms are both a challenge and an opportunity to observe how the ionosphere responds to space weather. And if you're just generally interested in how infrastructure responds to space weather, this is a chance to pay attention to how systems adapt. Satellites continue operating. Power grids remain stable. GPS stays functional. But all of those systems are actively managed during geomagnetic storms. Operators make adjustments. Engineers monitor performance. Redundancies kick in. That behind-the-scenes work is usually invisible to the public. But during a predicted storm like January 17th, it's worth recognizing that there are people tracking this event just as closely as aurora photographers are, satellite mission controllers watching drag increase, power grid managers monitoring geomagnetically induced currents, aviation authorities adjusting routes, all of it happening quietly, efficiently, and effectively. Because that's the reality of modern space weather preparedness. We've learned how to manage these events. We've built systems with space weather resilience in mind. We've developed forecasting capabilities that give us days of advance notice. And the result is that even when a Kindex 5 storm hits, the impacts are manageable. But here's the key, that manageability depends on awareness, on forecasting, on people like NOAA's space weather team tracking coronal holes through multiple rotations, predicting when high-speed solar wind streams will arrive, and providing accurate outlooks that allow everyone, from infrastructure operators to curious observers, to prepare. January 17th is a perfect demonstration of that. A storm that's been on the radar for weeks, a storm with a known source and predictable timing, a storm that, when it arrives, won't catch anyone off guard because the science is clear and the forecasts are reliable. So when the 17th comes, whether you're outside watching auroras, tracking real-time space weather data online, or simply going about your day while systems quietly adapt in the background, you're participating in something remarkable. You're watching the Sun and Earth interact on a planetary scale. You're seeing the effects of a coronal hole that's been rotating into position for weeks. You're experiencing the culmination of solar cycle 25's extended maximum, and you're doing it with complete clarity, because the patterns are understood, the forecasts are accurate, and the science is accessible. That's the transformation space weather forecasting has undergone over the past 2 decades. From vague warnings and unpredictable events, to pattern-based predictions and manageable impacts, from mystery to understanding. January 17th is evidence of that transformation, not a day to fear, but a day to watch, to observe, to understand, to appreciate the predictability that science has brought to what once seemed chaotic. But even as we focus on January 17th, it's important to remember that this isn't an isolated event. This is one moment in a much larger pattern, one storm in an extended period of solar activity that's going to continue for months. January 17th is one date, one storm, one rotation of a coronal hole that's been tracked for weeks. But it's not the end of the story. Because solar cycle 25's extended maximum isn't stopping after the 17th, it's continuing through the rest of January, through February, through most of 2026, and likely into early 2027. That's the nature of a double peak solar cycle. The activity doesn't ramp down quickly, it persists, it sustains, and that means recurrent geomagnetic activity, like the pattern we've been tracking with this coronal hole, is going to keep happening. The coronal hole responsible for January 17th might rotate through a 4th time, a 5th. As long as it remains stable, as long as the Sun's magnetic field structure maintains that open field configuration, it will continue sending high-speed solar wind streams toward Earth every 27 days, and each rotation will create another opportunity for geomagnetic activity. But even if this specific coronal hole eventually dissipates, others will form. That's how solar maximum works. Coronal holes appear, persist for weeks or months, and then fade as the Sun's magnetic field reorganizes. But during peak activity, new coronal holes form regularly, some in positions that face Earth, some that don't, and the ones that align with Earth's orbital path become the next sources of recurrent activity. That's the cycle within the cycle. Solar cycle 25 creates the conditions, coronal holes create the specific events, and 27-day rotation timing creates the predictability. So when we talk about January 17th, we're talking about a single data point in a much broader pattern. An important data point, yes, a strong one. But one moment in an extended period of elevated space weather that's defining this entire phase of solar cycle 25. And here's why that broader perspective matters. It reframes how we think about space weather, because it's not about surviving individual storms, it's about understanding that space weather is a constant dynamic interaction between the Sun and Earth. Most of the time, that interaction is quiet, stable, invisible. But during solar maximum, the interaction intensifies. The Sun becomes more active, the solar wind becomes more variable, geomagnetic storms become frequent, and our relationship with that space weather shifts from passive to active. We don't just experience it, we track it, predict it, prepare for it, and manage it. That shift is exactly what NOAA's 27-day outlooks represent. They're not warnings. They're information. They're saying, Here's what the sun is doing. Here's what we expect Earth's magnetosphere to encounter. Here's when it's likely to happen. Be aware. Be informed. Be prepared. And the response to that information is what makes modern space weather forecasting so valuable. Satellite operators adjust orbits. Power grid managers monitor systems. Aviation authorities reroute flights. Aurora photographers plan trips. Researchers position instruments to collect data. And the general public stays informed instead of confused. That's the balance. That's the goal. Not to eliminate space weather impacts, because we can't, but to understand them well enough that they stop being mysterious and start being manageable. January 17th embodies that balance. A storm that's been predicted for weeks. A storm with a known source and clear timing. A storm that, when it arrives, will create beautiful auroras, trigger minor operational adjustments, and demonstrate the effectiveness of pattern-based forecasting. And when the 17th passes, the pattern will continue. Another 27 days, another rotation, another chance to observe, understand, and appreciate the dynamic relationship between the sun and Earth. Because that's what space weather really is, not a threat, not a crisis, just physics. Natural interactions on a planetary scale that we've learned to measure, predict, and integrate into how we design and operate the technological systems that define modern life. Solar Cycle 25 is giving us an extended opportunity to engage with that physics, to watch coronal holes rotate, to see geomagnetic storms develop, to track auroras expanding, to understand how satellites, power grids, GPS and communication systems respond when space weather conditions shift from quiet to active. And the more we engage with that, the less intimidating it becomes. The more we understand the patterns, the less mysterious they seem. The more we watch the forecasts play out accurately, the more we trust the science. January 17th is a milestone in that ongoing engagement. A storm that confirms what the patterns predicted. A storm that demonstrates how far space weather forecasting has come. A storm that shows the value of watching, tracking, and understanding instead of fearing. So when the 17th arrives, take a moment to appreciate what's really happening. The sun, 150 million kilometers away, sending a stream of charged particles toward Earth at nearly 1 million kilometers per hour. Earth's magnetic field, generated by currents deep in the planet's core, reaching tens of thousands of kilometers into space to deflect and absorb that stream. The magnetosphere, compressing and releasing energy in cascades that create auroras, affect satellites, and ripple through technological systems. All of it predictable, all of it understandable, all of it part of a pattern that's been unfolding for weeks and will continue unfolding for months. That's the bigger picture. That's the story January 17th tells. Not a story of crisis, but a story of clarity, of science turning chaos into pattern, of understanding replacing fear, of humanity learning to read the sun's rhythms and integrate that knowledge into how we live, work, and build. And as Solar Cycle 25 continues through 2026 and into 2027, there will be more dates like January 17th, more coronal holes, more recurrent geomagnetic activity, more opportunities to watch, learn, and understand. So stay informed, keep watching the forecasts, track the patterns, pay attention to the 27-day cycles, notice when auroras expand, see how systems adapt, and appreciate the fact that space weather, for all its complexity, is becoming something we can actually understand and prepare for, because that's the transformation, that's the achievement, and January 17th is proof that it works. A storm predicted 10 days in advance, a storm with clear sources and measurable impacts, a storm that, when it arrives, will feel less like a surprise and more like confirmation of what the science already told us, and that clarity is everything. That's what turns space weather from something vague and unsettling into something concrete and manageable. That's what allows us to appreciate the beauty of auroras without fearing the disruptions. That's what lets us build resilient systems and trust that they'll adapt when conditions shift. January 17th, one date, one storm, one moment in the extended pattern of Solar Cycle 25. But a moment that demonstrates exactly how far we've come in understanding the sun, predicting its behavior, and living in harmony with the space weather it sends our way. Watch for it, track it, understand it, and when it arrives, you'll know exactly what you're seeing.